Hello everyone, in this video we'll be studying about the design of leaf springs. So leaf springs are the wide variety of springs that are made out of flat strips, and this semi-elliptical laminated spring is the best or common type of this leaf springs that we are using. And here you can see the semi-elliptical leaf springs which are bent into the form of the semi-ellipse, and you can see this one used in the suspension systems of automobiles and railway wagons. Here you can see in this figure, and its schematic diagram is shown here. So we'll be going to the details or detailed terminology of all these things, and then we will be analyzing this leaf spring for its design. So if you are observing this figure, this is showing you the picture of the semi-elliptical leaf spring, and in this one there will be a leaf called master leaf which is coming at the top, and ends of this is bent into form part called eye, and onto this one the supports will be coming. And just below the master leaf some leaf will be coming which are named as full length leaves, which are actually the length of this will be remaining same. That number of full length leaves may be 1 or 2 or 3. And below the full length leaves there will be leaves whose length are gradually getting reduced as we are going to the bottom, and these are known as graduated length leaves. So here you can see the master leaf at the top, and below the master leaf you can see the full length leaves, and below that you can see the number of graduated leaves. And all these leaves are bound together with the help of this bolt, and these are connected together. And here we will be naming, or the number of full length leaves will be named by IF, and the number of graduated length leaves will be named by IG. Then we are having the total number of leaves I equal to IG plus IF. So this is about the number of leaves. Next we will be looking onto the different forces and the stresses induced in this leaf spring for its design. So whenever we are taking or analyzing, there is a mistake in the data book. Actually it is given 2F in the equation, and the corresponding equations are given in terms. So there is a mismatch. So you have to, whatever be the central load acting on this leaf spring, that should be taken as, or that should be called as F. Then this reactions at this supports or at this I portions will be F by 2, F by 2. So only correction is the central load should be called as F instead of 2F. So we'll be looking on to the stresses induced in this leaf spring now. So I already mentioned this F is the centrally applied load. Then we have a distance L which is coming in the expression of this stresses, and that L will be taken as the distance from this I. So I means this portion up to the spring band. Spring band means this spring are bound together with the help of this U bolt, and the distance up to this bolt from the nearest eye. That means this distance will be called as L, and the same L will be used in equations to find the stresses. And another parameter is B dash. B dash is actually the width of the laminated spring. So if you are taking any of the spring, then you can get this shape, the isometric view you can see like this. So the width means this dimension, that is B dash. So we will be designating the width by B dash, and the thickness of this each flat strip or this laminated strip will be named as H. So B dash is the width and H is the thickness. So with this we will be seeing the stresses induced. So in data book you can see the equations which are required for this design of leaf spring. So we will be taking the central forces F, and this length between this I up to this band will be taken as L. Then we have stress in the full length leaves with no pre-stress. About pre-stress will be coming after this. So the stress in the full length leaves is given by equation 11.31a. That is this equation 9FL by B dash H square into 2IG plus 3IF. All terms that you are having. F is the centrally applied load. L is the distance from I to the band. B dash is the width of the spring. H is the thickness of each strip. And IG is the number of graduated leaves which is including the master leaf, and IF is the number of full length leaves. Similarly, you can find the stress induced in the graduated leaves using this expression 11.31b, and that will be giving you this expression. If you are observing, other than this coefficient 9 and 6 in these two equations, all other terms are same. That is FL by B dash H square into 2ig plus 3f. It is coming in both terms. So you can find a relation between sigma f and sigma g, that are the stresses induced in the full length and the graduated leaves, as like this one. That is, the stress induced in full length leaves will be 1.5 times the stress induced in graduated. Or in another way you can say the stress induced in full length leaves are 50% more than that of stress developed in the graduated leaves. So about this we'll be discussing the next phenomena called a nipping. So in usual case, this is the stress induced in full length is 50% more. So here we will be seeing the equalized stress in springs, or so called a nipping phenomena. So we are having the stress induced in full length is 50% more. So now next our aim will be to equalize the stresses in this all leaves to some same extent. That means in order to stress all the leaves to same extent, what we are doing, we will be giving a different radius of curvature for the different leaves. That means the radius of curvature provided for full length and graduated leaves will be different in order to equalize the stresses in both. That means you will be having the full length leaves which are coming at this position, and a further more curvature or lesser radius of curvature will be provided for the graduated leaves, so that the stresses will be getting equalized. And whenever you are doing this one, there will be a gap formed in between these leaves, in between these leaves, and that gap is known as nip, and it is represented by the letter C. So the expression for C, or what is the amount of gap produced in between leaf, it is called a nip, and you can find this using the expression 11.32a. So FL cube by I dash into H cube into E, where E is the Young's modulus. And this phenomena of equalizing the stress by providing different radius of curvature for full length and graduated leaves is known as nipping. So as a result of nipping, you will be having equalized stresses in both full length and graduated. So at that condition, you will be having sigma f equal to sigma g, and this is the expression you can find using this equation 11.32c. And there is another parameter may be asked in the problems for design of leaf springs, which are this one, the force induced in the bolts. That means you will be using this U bolt or the clips to connect this all strips together, so that this FB will be giving you the force induced in this bolt. So these are all the analysis of leaf springs. Now we will be using these equations to solve one problem in for this design of semi-elliptical leaf springs, and we will be seeing that problem solving in the next video.